All right, we're going to start off with a problem that appears in a couple of my practice exams. It's a car driving on a flat circular track. And I've drawn two views here. One of them is our top view. So this is like if we were in a helicopter up above here looking down, we would see the circular track, the car driving this way. And what I'm going to give you in the problem is the radius of the circular track and also the speed that the car is moving. And it's going to be a constant speed. What we're going to be using more is this side view. And so in this view, this is the car coming. This is a person standing by the circular track. They see a car come out and move along a semicircle here, go into the board, and do a semicircle and then come out. So hopefully that's making some sense here. All right, and what we're going to try to find is the minimum. Find the minimum coefficient of static friction in order for it to move in this circular motion without sliding. So, all right. Anyway, it has something to do with static friction, it seems like, and so we need to use our forces strategy. So we'll start off. We're going to use this picture here. In fact, I'm going to clear some space for myself here. And let's draw out our forces. We've got, of course, our force of gravity, and we've got a normal force. And here is actually where we need to do some thinking in this problem. We know that this object is accelerating. Even though it is moving at constant speed, it is accelerating because the direction of its motion is changing. And it's moving along this horizontal circle. And so right at this point in its motion, its acceleration is to the right in the picture, towards the center of the circle. So the circular trajectory here. Now, if it's accelerating in that direction, there has to be a net force in that direction. The net force and the acceleration always have the same direction. All right, so from Newton's second law over here, hopefully we can see that. Acceleration and net force always have the same direction. I know it's accelerating in this direction, so there must be a net force in that direction. So, well, we've already got gravity. We've already got a normal force. There's no ropes or strings attached here, and so we're left with friction. Now, the car is moving, but unless we're doing some drifting here, it's not going to be sliding. The wheels are going to be rolling without slipping here. And in that case, since it's not sliding, it's actually static friction. Now, what do we know about the direction of static friction? Static friction must point parallel to the surface where the car is in contact with the ground, so parallel with the ground. And it's going to point in whatever direction it needs to so that the object doesn't slide. And in this case, it must point towards the center of the circle, because that is the only force that can point in that direction. And again, we know that that force is in that direction. All right, so what, we're going to choose our coordinate axis, and we're just going to use a standard XY coordinate axis here, and now we're ready to apply Newton's second law in both the x and y directions. Let's go ahead and start in the y direction here. And in our vertical direction, our y direction, there's actually no motion at all. Okay, we've got this car moving in a horizontal circle. There's no motion at all, and so we can conclude that there's no acceleration here. This is going to be 0. And so our forces, we're going to go through and add up all the y components. We have a positive f sub n. The force of gravity is in our negative y direction, and I'm just going to skip a step and write mg, because that's always the magnitude of a gravitational force. The static friction force doesn't have a y component, so this is it. Well, okay, great. We can get this result. The normal force is equal to the weight. It's one of those problems where they are equal. Actually, m isn't given in this problem, so we can't proceed any further with this alone. Anyway, we're going to hang on to that result, and now let's take a look at some of the forces in the x direction. I guess I'll use some space here. And in the x direction, well, actually these two forces don't have any x component, and so we just have our static friction force pointing, it doesn't come on, in the positive x direction. Now over here, just like we had some special information about a sub y, that was 0, we also have some special information about a sub x. Because our x component in the picture is that way, and I know when an object moves in a horizontal circle here, it's going to have this acceleration towards the center, this centripetal acceleration, and the amount is v squared over r. Now again, there's no extra hints when we read a problem like this. It just says it's moving along a circular track, and we have to know this. At this point, it looks, let's take a look. We've got two things we don't know over here. We still don't know the mass, and we've picked up another unknown. Both the speed and the radius of the circular track we know. So we have 3 unknowns and only 2 equations. Fortunately, we do have more information. It's not the equation, it's this inequality. And I guess we should know to use this because it's the only place, if we're going to find out something about mu sub s, the coefficient of static friction, this is the only place that it appears. And so at this point, we have, for my normal force, I can just plug in this, and for my static friction force, I can just plug in this here. So let's just see what happens. And we can divide by some non-negative numbers here, some positive numbers. We can divide both sides of the inequality by m. And it looks like I think I want to find out as much as I can about mu sub s. So let me divide both sides by g. And so what I'm going to conclude here is this. And now our final argument is we want to find the minimum value of mu sub s. In other words, the minimum value of the roughness of those surfaces. If the surfaces aren't very rough, if it's too smooth, then this car will slide and it's not going to move in this circular path. Now, mu sub s must be greater than or equal to this number. We can calculate this number, right? Because we have all of the quantities here. And so the smallest value, the minimum value, is when they are equal.